Good morning, ladies and gentlemen. Hope you had a good day yesterday. We're going to get back to work, and we're going to start talking about some bases and some calculations. So last class we talked about calculating pHs of strong acids and weak acids. Today we're going to deal with strong bases and weak bases. But what's kind of nice is really they're the same thing, all right? But instead of worrying about concentration of H pluses, well, we're still worrying about concentration of H pluses because we're doing pH, right? We'll be playing with OH minuses too, right? So now, if we have a strong base, this is telling us that it completely dissociates in water. Okay, so let's say that I have a 0.10 molar solution of NaOH. Okay, NaOH is a strong base, so NaOH would completely dissociate into Na plus and OH minus. So if we do a quick ice table, right, if we're starting with 0.10 molar and none of this and none of this, this is going to completely go over here, so this will be minus 0.10 molar, and we'll end up with none of this, and then we'll have, this will go up 0.10 molar, and this will go up 0.10 molar. So this concentration is 0.10 molar, and the OH minus concentration is 0.10 molar. Right, so here's my concentration of OH minus. My POH is equal to the negative log of the concentration of OH minus. So my POH is equal to the negative log of 0.10 molar. And we end up with a POH of 1.00. Now, we really don't work in POH concentrations very often. We work in H plus concentrations. So generally what you'll have to do is you'll have to calculate the pH from this, right? And you can do that a couple ways, but the easiest way, remember, is pH plus POH equals 14. So the pH plus 1 equals 14. So our pH is equal to, we should probably put some sig figs in here, 13.00, which this is just telling us that it's very basic, which is what we expected. Okay, so there's lots of calculations we can do with this. Let's try another one. Let's calculate the pH of a solution prepared by dissolving 2.0 grams of barium hydroxide in 1.0 liters of water. And I'm going to give you the molar mass so we don't have to calculate it. The molar mass is 171.3 grams per mole. 171. All right. So we're taking barium hydroxide and we're dissolving it into water. All right. Well, the first thing you need to know is how many moles of barium hydroxide we have. So we have to convert to moles. Number of moles equals given mass over gram formula mass. Right, and we got 2.0 grams, and I gave you the molar mass so we didn't have to calculate it. which is 1.713 grams per mole, and that equals 0.012 moles. All right, so there's my how many moles of barium hydroxide. Now we need to know the concentration. Molarity equals moles over liters. Well, we have 0.012 moles in 1.0 liters. So it turns out that we have a 0.012 molar solution of BaOH2. Right, now, let's write the dissociation equation of BaOH2. So if we take BaOH2 solid and we dissolve it in water, we will get Ba plus 2 aqueous plus 2 OH minus aqueous. Okay, now barium hydroxide is a strong base, so it will completely ionize. Right, so if we do our quick ice table, right, we're starting with 0.012 molar. Right, this is 0, this is 0. This is going to go down by 0.012. This is going to go up by 0.012. And this is going to go up 2 times 0.012. So this ends up being 0, this ends up being 0.012, and this ends up being 0.024. These are all molar solutions. All right, so you have to be careful with your stoichiometry in here, because for every one of these, we're making 2 of these. Now we could just say POH is equal to negative log of the concentration of OH minus, which is right here, negative log of 0.024, and that is 1.62, and that's our POH. Our pH is equal to 14.00 minus POH. I just rearranged that equation. So our pH ends up equaling 12.4. Right, so this is not as quite as basic as the NaOH we just did. Right, but these are some typical calculations that you'll have to make. All right, let's try this, and this is something a little bit new. All right, so let's say we have 50.0 milliliters of a 0.0921 molar BaOH2 solution. So we have this solution, and it is diluted with enough water to make 250.0 milliliters of solution. Calculate the pH of the diluted solution. So we're taking this solution and we're diluting it down, right? So we're going to add water. And we're going to use this equation, M1V1 equals M2V2. And you should have used this in the lab that we just did. All right, and this is the dilution equation. So this is the molarity of the first solution times the volume of this first solution equals the molarity of the second times the volume of the second. So this is just a nice, easy little equation. So our original molarity was 0.0921 molar. And our volume was 50 milliliters, and we can be in milliliters here as long as it's the same on both sides. All right, so 50.0 milliliters equals, we want to know what the new molarity is when we dilute the volume down to 250.0 milliliters. When we do that, we get a 0.0184 molar solution. All right, so this is the diluted barium hydroxide solution. And this turns, now that we've done this, this turns into the same exact problem we just did. Our BaOH2 goes to Ba plus 2's aqueous plus 2 OH minus aqueous. All right, so if we do our ice tables, we have 0.0184. It's going to go down by 0.0184. We have none of this, and we have none of this. This is going to go up by 0.0184. This is going to go up by 2 times 0.0184. So this will be 0. This will be 0.0184. And this turns out to be 0.0368 molar. So now we can go ahead and do some calculations. pOH equals the negative log of the concentration of OH minus. Negative log of 0.0368, and that gives us a pOH of 1.43. pH equals 14.00 minus 1.43. Our pH is equal to 12.57. And that's what our pH would be. I really did this problem really just so you could see this dilution equation and how to use it real quick. All right. Well, let's get into weak bases. So we know if it's a weak base, it will not completely ionize. When you put it in water. So when a weak base dissolves, it will accept a proton from water. So a general equation for a weak base is we get B, there's my weak base. We put it in water, liquid, and we get BH plus, because it's taking a hydrogen, and OH minus. Okay, this is aqueous, and this is aqueous. Now that we're in weak bases, we can calculate what's called Kb. Just like we had a Ka, Kb is the base dissociation constant. And it's the same way. Kb is going to equal our concentration of the BH plus times the concentration of OH minus all over, this doesn't count, concentration of B. So we're going to assume the concentration of H2O is constant. And it is at temperature. As long as we don't play around with temperature, we're in good shape. So Kb is our base dissociation constant. Now, sick of blue. Let's go to a different color. The larger the Kb, the stronger the base. So if Kb is very strong, if Kb is very large, all right, it's going to be a very strong base, and the equilibrium is going to rest over here. If Kb is small, okay, if that equilibrium constant is small, all right, it's a weak base, and it'll lie over here. Now, there are really two classes of weak bases. The first type are nitrogen-containing molecules. Okay, so if they have an NH3 on there somehow, all right, it's going to be a base. And then the other type of weak base is the anions of weak acids. Now, remember when we talked about conjugate acids and bases? The weaker the acid, the stronger the base. Okay, so okay, now just because it's stronger doesn't mean it's a strong. Okay, this doesn't mean that it's a strong base. Okay, so be careful with that. I'm not saying that it's going to completely dissociate. I'm just saying the weaker the acid is, the stronger the base is going to be. Okay, so, and in reality, the conjugate base of a weak acid is a weak base. Okay, so if you have a weak acid, its conjugate base is going to also be weak. Okay. Which brings us to this equation. Kw, okay, our water ionization constant, ends up equaling Ka times Kb. And we're going to be using this relationship. All right. Let's go ahead and do a calculation with a weak base. This is calculating pH of weak bases. So let's just go ahead and do one. Calculate the pH of 1.5 molar solution of NH3 of ammonia. Kb is equal to 1.8 times 10 to the minus fifth. That's a 5. All right, now this is really the same exact type of problem as we did before with our weak acids. All right, so we need to first write out the equation. So NH3 plus water will form an equilibrium. And remember, this base is going to take a hydrogen. It's going to accept a proton. So it becomes NH4 plus aqueous plus OH minus aqueous. Now, just like we did before, we have to compare KB and KW. If KB is greater than KW, that means the OH minus comes from the base. Because remember, if we have water at all, it dissociates on its own to H plus and OH minus. Not much, right? That's where our KW comes in, but it does. So we want to know in this equation, is this OH minus coming from this, or is the majority of it coming from this? And if the KB is greater than the KW, that tells us our OH minus is coming from our base. Now, if KW is greater than KB, that tells me that the base is not making any OH minus. And in reality, if KW is greater than KB, the pH of the solution has to be what? It's got to be neutral. Because remember, KW equals a concentration of H plus times the concentration of OH minus. All right, if all of the OH minus is coming from the KW, all right, that means that this has to have a pH of 7. All right, that's kind of like a trick question, so just be careful with that. All right, normally you're going to be here. All right, now if we look at ours, our KB is equal to 1.8 times 10 to the minus 5th, which is much greater than our 1.0 times 10 to the minus 14th. All right, so we know that our OH minus is coming from our ammonia. Next, let's set up an ice table. This is not going to matter because it's constant. All right, this is 1.5 molar. It's going to go down by x, so this is 1.5 minus x. This is 0, this is 0, this is plus x, this is plus x, so this is going to be x and x. Now let's write our equilibrium expression. KB is going to equal the concentration of NH4 plus times the concentration of OH minus all over the concentration of NH3. Our KB was 1.8 times 10 to the minus 5th equals the concentration of NH4 x times the concentration of OH minus, which is x, all over 1.5 minus x. Now, just like we did before, okay, just like we did with the weak acids, does this really change? Well, a very small amount of it is going over here. So we're going to assume x is negligible over here. So we're going to assume that x, okay, for ammonia is negligible. So that changes our equation into 1.8 times 10 to the minus 5th equals x squared all over 1.5. So when we do that math, X ends up being 5.2 times 10 to the minus third molar. And this is our OH minus concentration. Now, just like we did with the acids, we need to check. All right, because the percent has to be less than 5%, just like before. So the next thing we're going to do, okay, is we're going to check. We're going to say, hey, look, we got part over whole times 100. Our part was 5.2 times 10 to the minus third over 1.5 times 100, and we get 0.35%, which is way below the 5%. Okay, so that's less than 5%. So our assumption is good. So we're okay. All right, well, now that we know that this number is good, we can go ahead and calculate our POH and then our pH. So POH equals the negative log of the concentration of OH minus. POH equals negative log of 5.2 times 10 to the minus third molar. And that is 2.28. pH equals 14.00 minus the POH. So pH equals 14.00 minus 2.28, which gives us a pH of 11.72. 11.72. Okay. Again, really similar to what we just did with acids. All right, now, are you asking yourself, is there a shortcut? And there is. All right, just like acids, weak bases work the same way. All right, there is a shortcut. If the concentration of the weak base is greater than 1,000 times the Kb, all right, just like before, we can use the concentration of OH minus is equal to the square root of the concentration of the base times Kb. So if this is true, we can use this equation. All right, so let's do that same exact problem that we just did this way with the shortcut. Calculate pH of a 1.5 molar solution of NH3. And remember, our Kb was equal to 1.8 times 10 to the minus fifth. All right, well, let's check. Is 1.5 molar greater than 1,000 times our Kb of 1.8 times 10 to the minus fifth? Well, that's a yes, so we can use the shortcut. So the concentration of OH minus is going to equal the square root of 1.5 times 1.8 times 10 to the minus fifth. So our concentration equals 5.2 times 10 to the minus third. Which is the same thing that we got last time, which means our POH was equal to 2.28, and our pH was equal to 11.7. This is the same as we calculated before. Now, what if it's not? What if it's not? What if the OH concentration is not 1,000 times greater than Kb? Well, guess what you're going to be back using? Yes, you're going to have to use the quadratic equation. Do I think you're going to have to do that? No. So will this work almost all the time? Yes. All right, we got one last thing that I want to talk about today. So we've talked about our strong acids, talked about strong bases, we've talked about weak acids and weak bases. The next thing I kind of want to talk about next are diprotic acids. We've talked about monoprotic acids, but we need to talk about diprotic acids. If we look at the word diprotic, di means two, protic means protons. So these are acids that will produce 2 protons in solution. These will produce 2 protons in solution. Example is H2SO4. Right? H2SO4 is a diprotic acid. It will produce 2 H pluses in solution. Now, there are 2 dissociations that happen here. All right, the H's come off one at a time. So our first dissociation is this. H2SO4 goes to H plus plus HSO4 minus 1. The Ka for this is very, very large. What does that tell me? If the Ka is very, very large, that means it's a strong acid, and it's going to basically all come over here. All right, so this is a strong acid. Now, the second dissociation. Is this HSO4 minus 1 is going to produce another H plus aqueous and SO4 minus 2 aqueous. Now, the Ka for this is 1.2 times 10 to the minus third. What does that tell me? Well, it tells me that my second dissociation is weak. So am I going to produce a lot of H plus the second time? And the answer is no. All right, so we're going to, most of our H plus is up here, and then we'll produce just a little bit more H plus. All right, so this step acts like a weak acid. When we are calculating the H plus concentration, we must account for both dissociations. Okay. So what we'll do is we're going to add the concentration of H plus from our first and the concentration of H plus for the second to get our total H plus concentration, okay, in this diprotic acid. All right, I want to show you one. All right, we'll use H2SO4. Calculate the pH of a 2.0 molar H2SO4 solution. First step we know is strong. Okay, so this first one is a strong acid. So we know that H2SO4 is going to completely dissociate into H plus and HSO4 minus 1. These are both aqueuses. All right, so our Ka is very large. So if we're starting with 2.0 molar of this is all going to come over here. So the concentration of H plus is going to be 2.0 molar, and the concentration of HSO4 minus 1 is also going to be 2.0 molar. Okay. Now, our second step. HSO4 minus aqueous is going to be in equilibrium with H plus aqueous and SO4 minus 2 aqueous. And the Ka for this one is 1.2 times 10 to the minus third. Right? And this is acting as a weak. This is acting as a weak acid. Now, I'm going to do this with the shortcut. All right? So if I compare my Kw and my Ka, 1.0 times 10 to the minus 14th, 1.2 times 10 to the minus third, oh no, that's not what I want to do, sorry. My Ka is my acid concentration greater than 1,000 times the Ka. Well, my acid concentration, remember, is 2.0. Is that 1,000 times greater than 1.2 times 10 to the minus third? And the answer is yes. So I can use the shortcut. So the concentration of H plus is equal to the concentration of our acid times the Ka. So we end up with the square root of 2.0 times 1.2 times 10 to the minus third, and that equals 4.9 times 10 to the minus second molar. This is the second H plus concentration. That's what's being produced over here. So to get my concentration overall, I add the H plus of the first plus the H plus of the second. So I have 2.0 molar plus 2.0, plus 4.9 times 10 to the minus second, and that gives me 2.049 molar. Okay, and this is my H plus concentration total. Now, if I do pH of this, it's a negative log the concentration of H plus. To use this, 2.049 molar. It's a negative log of 2.094, and my pH ends up being a negative 0.31. And you read the article on negative pHs. Right? If you have a concentration greater than H plus concentration greater than 1 molar, all right, it's going to have a negative pH, and that's okay. All right, now, so this is my pH. Just for fun. Just for fun. Let's stick in, what is the concentration of, what's the pH if it was just 2 molar? All right, because I want you to see what the second one really does to the pH. Okay, so what does that really do for us? So if we take the negative log of this, we get negative 0.30. So how much does it change the pH, that second step? All right, it's changing it very, 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 very little. Are we adding a little bit of H plus? Yes. All right, but it's very minute. Right, we're only adding a little bit more H pluses. Okay, so it changes the pH very little, but it does. Okay, now I want to mention triprotics. Okay, I just want to mention I'm not going to do an equation. I'm not going to do a problem with them. Triprotics. 3 protons. Example, H3PO4. All right, this is a triprotic acid. All right, we're not going to go there with a problem with this right now. We're going to be dealing with some triprotics later. All right, but I just wanted to bring it up. All right, so that you know what your monoprotic, diprotic, and triprotic acids are. All right, so that's all that we're going to do for today, and I will see you again tomorrow.